Hello everyone. Our topic is the forensic engineering analysis of the Eschede high-speed train disaster. We focused on how a fatigue failure combined with inspection limitations and organizational factors escalated into a catastrophic accident. We will briefly introduce the event, the investigation approach, and then move to findings and recommendations. The Eschede train disaster occurred on 3rd June 1998 near Eschede in Lower Saxon, Germany. The ICE 884 was traveling at about 200 km per hour on the Hanover-Hamburg line when a mechanical failure occurred in the first carriage. The train derailed and collided with a constructed road bridge, which collapsed onto the train and greatly increased the severity of the accident. Figure 1.1 shows the accident site and the scale of destruction. In total, 101 people died and 18 were seriously injured. Eschede is a classic forensic engineering case because it shows how a single component failure can trigger a system-wide catastrophe. The initiation failure was hidden inside a complex wheel system, so it was not immediately obvious. The case was also demonstrated that failures cannot be explained by materials alone. Design choices, inspection capability, and organizational decisions making all interact, which is why forensic engineering investigations both physical evidence and surrounding maintenance and safety processes.
Our literature review is based on a few key sources. Esslinger and co-authors provide the main technical analysis of the Eschede wheel failure and identify fatigue crack growth as the governing mechanism. Richard adds fracture mechanics insights and explains why rubber-sprung wheels can develop critical stress concentrations. Suresh provides the fundamental fatigue framework. Cracks can initiate and grow under cyclic stresses even below yield strength over many cycles. Ekberg and Cabo describe realistic railway wheel loading. Rolling contact combined with bending and vibration creates a fatigue-critical environment. Finally, Zerbst and colleagues highlight why inspection strategies must be linked to crack growth and detectability, otherwise critical defects can be missed. These are our main references for the technical explanation and the forensic interpretation. We also used several additional papers to support specific details, and all of them are listed in the report's reference section.
The investigation followed a structured forensic approach. Investigators began with a site survey and debris mapping to reconstruct the sequence of events without early bias. Evidence preservation was critical. Wheel sets were secured for laboratory analysis, and operational data such as speed records, maintenance history, and inspection logs were collected. The failure component was the rubber-sprung wheel, known as the Bochum 84 design. It consists of a steel wheel center, rubber damping element, and an outer steel tire. The design reduces noise and vibration, but it also after the stress distribution compared to the monoblock wheel.
In service, railway wheels experience complex cyclic loading. Rolling contact at the wheel, rail interface bending from vertical and lateral forces, and vibration creating fluctuating stresses over millions of cycles. This is exactly the environment where high cycle fatigue develops. To prove fatigue and reconstruct the failure, investigators use a combination of methods: visual inspection to locate crack origin and identify beach marks, SEM fractography to detect fatigue striations that confirm cyclic crack growth, and non-destructive testing, such as ultrasonic and eddy current methods. For forensic quality, evidence handling is essential. Fracture surfaces must be preserved, and samples are taken from initiation, propagation, and final fracture zones. Documentation and chain of custody ensure the results remain reliable and defensible. With that, we move to the findings.
Our findings show the wheel tire failed by fatigue, not by a sudden overload or impact. The fracture is circumferential and indicates progressive damage accumulation. The crack initiated at the inner surface of the wheel tire, which is consistent with the region of high tensile stresses during high-speed operation. Beach marks on the fracture surface show long-term crack growth over time. At the point of final failure, the crack had reached roughly 80% of the tire thickness, leaving only a small remaining ligament that could no longer carry the operational loads. Microscopically, fatigue striations confirm stable cyclic crack propagation, and importantly, no material or manufacturing defects were identified at the initiation site. This supports a service-indicated fatigue process rather than a production flow. The immediate cause was the fatigue fracture of the wheel tire after the crack grew to a critical size. The key forensic question is why it was not detected earlier. First, the crack initiated at an internal location on the inner surface. This is not visible during routine visual inspections, yet visual checks were the primary inspection method. Second, inspection capability had technical limits. Ultrasonic testing on mounted wheel sets can have reduced sensitivity because the axle wheel interface attenuates the signal. This means smaller cracks may not be detected reliably, especially if inspection intervals are long. On top of that, organizational factors contributed. Warning signs such as noise and vibration were not interpreted and escalated as indicators of imminent failure. Overall, Eschede is a classic forensic engineering case because multiple layers, technical inspection related and organizational, failed together.
To conclude, the Eschede accident demonstrates that the catastrophic failures rarely come from a single defect. Material quality was adequate and there was no evidence of manufacturing defects at the crack initiation site. The failure developed as a predictable fatigue process under normal service loading with long-term crack growth at an internal location. The disaster occurred because the damage remained undetected due to inspection limitations and was compounded by organizational decision-making and delayed response to warning signs. The core forensic lesson is to analyze the whole system: component, design, inspection, capability, and organizational process. Our first recommendation focuses on engineering and design. Innovative wheel concepts must be supported by design rules that reflect their real mechanical behavior. In safety-critical components, we should apply damage-tolerant design principles, meaning we assume cracks can exist and still ensure safe operation. This requires realistic service load measurements and three-dimensional simulations to identify critical stress regions early. Based on that, safe limits such as minimum tire thickness and reprofiling criteria should be defined using fracture mechanics considerations, not only geometric limits. Second, inspection and maintenance strategies must be adapted to fatigue crack growth. Fixed time-based routines alone are not sufficient. Inspection intervals should be linked to expected crack growth behavior, especially in high-risk regions where cracks initiate internally. In addition, NDT procedures must account for detectability limits. For mounted wheel sets, ultrasonic sensitivity can be reduced due to signal attenuation at the axle wheel interface, so inspection procedures and thresholds must be validated for the actual assembly. The goal is to detect cracks well before they reach critical size. Third, safety and regulation must evolve alongside technological innovation. New component concepts should only be approved after realistic load measurements and fracture mechanics-based damage tolerance evaluations. Regulatory frameworks should standardize inspection requirements for high-speed wheels, both the methods and the intervals, and strengthen reporting and escalation procedures when warning signs such as abnormal noise or vibration occur. Overall, Eschede shows that safety depends on design, inspection, and organization working together.
Thank you very much for your attention. If you have any questions, feel free to leave them in the comments below.